I'm going to continue with the decomposition methods, and this time we begin with a discussion of inequality constraints. Last time we talked about the case when everything was equality. So the problem under consideration is the minimization of Cx subject to Ax less than or equal to P. This was equality before. Okay, so that's the only difference. And X is, as before, it's a specially structured set. It's a polyhedral set. So that this will give a subproblem. Subproblems become easy to solve. And I'm going to still assume that X is bounded. So let's make that assumption. And what we do is we transform this problem into a master problem by first looking at extreme points of X. And let's just assume we enumerated them as, say, x1 up to whatever, xt. Okay? So a convex combination of these extreme points will give you any point inside capital X. And we represent any such x in X as a convex combination of these points using, say, multipliers lambda j, where lambdas add up to 1, and each lambda is a number between 0 and 1. Since the summation is equal to 1, non-negativity is enough here. They are necessarily less than or equal to 1. So with that, when you transform the problem, in place of x, if you write the expression lambda j xj, then you obtain the following master problem. Minimization of C cap j lambda j, j going from 1 to t, subject to Ax less than or equal to b becomes Aj cap lambda j less than or equal to b. And of course, we also have lambda j adding up to 1, with all lambdas being non-negative. Now, this is the master problem, except that, well, before doing anything with it, let's just recall what the A cap and C caps are. Cj cap, by definition, is the original cost vector times the jth extreme point. So this is the value of the objective function at the jth extreme point. And Aj cap is simply the column obtained by pre-multiplying the jth extreme point by A. That's the image of the jth extreme point under A. Okay? So, all right. So this is the master problem, except that I'm going to transform the master problem into the standard form. So we're going to add slacks here. So that the first set of constraints, let me write the slacks at the front here. That's better. So you just add m slack variables, assuming that the original problem has m rows and columns. Okay, so the master problem still has m rows here plus one additional row for the normalization of the lambdas, and we add a vector of slack variables consisting of m slacks plus lambda j's adding up to 1, and non-negativity on s and lambda together. take lambda to be the vector of the lambda j's. S is the vector of slacks. So this is the master problem that I'm going to use. The only difference of this from the initial one that we used for equality is the inclusion of the slacks here. That's the only difference. So there's really nothing mysterious here. And so given a revised simplex tableau defined by some basis whose inverse is here, okay, we again take a given basic feasible solution. The right side is, say, B bar. The objective value is Z bar. And you have, again, W alpha being the simplex multipliers or the dual variables, where A here is, of course, if you look at the matrix of coefficients here, you've got identity, and then you've got a 1 cap up to a T cap, zeros here, and then ones here. That's the matrix of coefficients corresponding to the constraints here. Okay. Now the first portion here has m variables. That's the dual vector W. Each component Wi here is associated with a constraint, or with the ith row of that matrix. The last row is the dual variable associated with the last row is alpha. Okay, so W is n. This part is an m vector. This is 1 by 1. This one is 1 by m. The other one is 1 by 1. Okay. All right. So the reduced costs need to be computed. Now, when you look at the reduced cost, we now need to compute the reduced cost both for slacks as well as lambdas. So if I denote the reduced cost for the jth variable, say lambda j, by this, the reduced cost for that is how much? It's going to be W alpha times AJ cap 1 minus CJ cap you take the dual simplex multipliers, multiply it with the jth column in the second part here. Okay. There's a lambda j somewhere in the jth column, so we're just picking that particular one and doing this operation, which gives you, this is the same as old stuff, so this will be W AJ cap plus alpha minus CJ cap, which upon simplification, if you put the original values of AJ cap and CJ cap, it will be simply this. So this is the same as before. And finding a maximum of these will be will correspond to solving a subproblem. But before I do that, let me also compute the reduced cost for the ith slack variable, say r sub s sub I. So this is for lambdas. All right. So in this case, W alpha times, now the column associated with the ith slack variables, these are the slack variables here, so Si will be here somewhere, okay? The ith column here. In that case, its column will be a unit vector, Ei, that's the, from the identity. And at the bottom, you have 0 rather than 1. All right, so, and the cost for slack is 0, the original cost, okay? See? You have no cost here for the slacks. All right, for this reason, it will simply, now W times EI will pick up WI. You're just pre-multiplying a W vector with a unit vector, so it just picks up the ith component of that. And alpha times 0 is 0, so this is just WI. So here's the conclusion. This is for I going from 1 to M, whereas the other one is, of course, J going from 1 to T. Okay? The other one is numerous. This one is manageable. All right, so if Wi happens to be a positive number in the dual simplex multipliers, then the conclusion is Si enters or can enter. Okay? If you have more than one such Wi that are positive, choose any one you wish. If Wi are less than or equal to 0 for all I, then we need to still look for the maximum reduced cost associated with the lambdas. So we solve, in that case, we look for the maximum reduced cost defined here, which amounts to solving maximization of WA minus C times X, where X is an unknown vector, except that at the optimum it will pick up the appropriate extreme point. So, this defines that sort of a subproblem. Except I need to also add alpha to the objective function value. Okay, so solve this if alpha plus, or let's just say, suppose some extreme point, say x bar, solves the subproblem. Let's just call the subproblem defined by W alpha. Okay. If suppose x bar solves the subproblem SPW alpha, if R bar, which is the objective value you get for this, if this is less than or equal to 0, yes, we're optimal. The old master problem solution is optimal. Else, R bar is positive, X bar or lambda bar corresponding to X bar enters. Okay? Lambda bar is the multiplier lambda associated with that particular extreme point. So before doing anything else, you need to compute the appropriate y vector, which is your B inverse times A times X bar, which is the, column associated with that extreme point. And you form, after that, let me just continue here, you form, or you put that column next to your tableau. This is the same old tableau. You put this column with reduced cost at the top, y bar here. This is the entering column. We just generated it. And then what do? You look at the usual ratios, the elements of B bar divided by the appropriate corresponding elements of Y bar, assuming that this is this has at least one positive entry. By the way, this is the unbound, this is the, sorry, by assumption, capital X is assumed to be bounded here, so this cannot have unbounded solution in this assumption, okay? So for this reason, you're not going to encounter an unboundedness situation here. This will give you an appropriate ratio which will tell you which lambda to exit or which S to exit, which slack to exit. And after that, you will know how to continue just by updating. How do you update? You pivot on the appropriate element. You get the new inverse. You get the new W and alpha, etc. And then you just do everything relative to the new basis. Question?
All y bars then be positive, right? Not unbounded.
No. They won't be positive. They will not be non-positive. There's a difference, okay? Meaning that it will have at least one component which is positive. Otherwise, of course, it would be unbounded, okay? This is not a, y bar less than or equal to 0 is not a possibility. But the negation of this does not mean y bar is positive, okay? Okay, so it's not really difficult. In fact, it gets to be a bit easier because as soon as you have a wi that's positive, you don't even need to solve a sub-problem here. You can immediately enter that, okay? So before I continue with the unbounded X case, let me address the question of how we find an initiating basic feasible solution for both cases. So in this case, I'm still assuming X is bounded by assumption. There are two cases. One is the case when AX is less than or equal to B in the original problem. The other one is the case when AX is equal to B. Okay? I covered AX equals B case first. However, I'm going to supply the initiating basic feasible solution for the second case first, and then we'll look at this one. Okay? So in this case, the master problem has the following. What else do I have? I have summation lambda j equals 1. And then everything is non-negative. Okay? This is the standard form master problem corresponding to AX less than or equal to B type of constraints in the original problem. All right. Now, here I've got m constraints. Here I've got 1 constraint. So I need a basis of m plus 1 by m plus 1. Okay? And the natural thing to do is to pick the s's as your basic variables, but you have one less than you need. You've got m s's here, m slacks, but you need one more because you need a lambda here for the last one. Okay, so you use the slacks and some lambda j, you need exactly one such lambda j as initial basic variables if there is a extreme point xj that you know of such that a times xj is less than or equal to b. If there's an extreme point of x, if there's an extreme point xj of x such that this is true. So, in that case, the constraints will look like S plus. You will pick up that particular lambda j. The other ones will be non-basic, so you will have 0, and it will have axj lambda j in that case. And this part is less or equal to 0, so the right side will be how much? Well, it will be equal to b. Let me see. Which means that S is equal to, yeah. In this case, of course, this implies S is equal to b minus a times xj. But axj is less than or equal to b, so all the s's are non-negative. That's what we were looking for. Okay, so this is a feasible basic solution if you know that this is the situation. All right, so S and lambda j is non-negative and satisfies. Of course, lambda j will be 1 in this case, okay? Satisfies the constraints of the problem, of the master problem, with S being equal to b minus a times xj and lambda j being equal to 1. The other lambdas are 0. Okay. In this case, of course, your initial B inverse, let's compute that. How much is B inverse? In this case, B is identity corresponding to the slacks. And then we have A times xj corresponding to lambda j column. We have 0 here. We have, what do we have here? We have a 1 here, okay, in that column. So B inverse is easy to get. It will have identity 0 minus axj and 1. Am I right? Let me see. I times I. So what is B inverse B? Let's just check it. Do a quick check. I times I plus axj times 0. So this will be I when you multiply. And then I times minus axj plus axj times 1, which gives you 0. For that part, you want a 0. And then what? 0 times identity, there's some, 0 times identity is 0. And then 1 times 1 times 1. Yeah, you have a 1. Yeah. So it seems correct. This part disappears. Okay, it becomes 0. So you have an n plus 1 identity. All right. So your B inverse is identity minus axj 0, 1, like that. What is this part? Well, you can compute it. Let's just do it. B inverse times BM1. What is the output of this? B plus or minus AXJ. So this is B minus AXJ, which is, of course, the values of S. It agrees with that. The second part is 1. Yeah. What about W's? W alpha is CB cap times B inverse. What is CB cap in this case? Slacks have 0 cost. The other one has CXJ as its cost. That's the cost of lambda. Times B inverse. So the output of this will be 0. And then 0 CXJ. That's what I've got. So you have a big vector of zeros here with a last component, CXJ. Alpha is your CXJ. And the objective value, Z bar, is equal to CB cap times B bar, which is 0 CXJ times B bar is B minus AXJ 1. 0 times that plus it's CXJ simply. Okay. All right, so that's the easy case. If you know, if there is an extreme point that you know of which satisfies the original constraints. If not, then this is what you do. So in that case, you just pick an extreme point, which you arbitrarily label as x1. So you pick an extreme point, say x1 of x, and rewrite ax less than or equal to b in the form. Well, what is the idea here? You're going to use x1 like you used it here, like the xj you used here, except that you don't know if x1 fulfills the less than or equal to constraint here, less than or equal to condition. So typically, of course, if x1 satisfies that, you're back to this situation. If it doesn't, this is violated in at least one constraint, or in at least one inequality, which means that at least one component of the S vector will be less than 0. Okay? In that case, what you do is you write your constraints in this form, except that it will not work. Okay? So this satisfies the first part of the constraints. Which may cause some components of S to become negative, since S is, by definition, B minus AX1 times lambda 1. Lambda 1 will be 1. That's going to be the value, and there's no guarantee that this will be greater or equal to 0. In general, if this is not satisfied, you will have at least one component which turns negative. Okay? Of course, if this is not the case, then use x1 for xj in the previous discussion. So, whenever this is the situation, what else do we do? Multiply the equations in this by minus 1 as necessary, meaning that whichever components turned negative here, you identify those rows, multiply them by minus 1, so that things become, or the constraints are written in a different way, so that rather than having AX less than or equal to B, you have now sometimes greater than or equal to type constraints because you multiplied by minus 1. Then insert as many artificial variables as necessary for such constraints, those that are multiplied by minus 1, and use phase 1. Minimize the sum of the artificial variables to obtain a basic feasible solution at the end of phase 1. Okay? The case of AX equals B is similar. In this case, we have really nothing to start with. It's just too complicated. Add up to n plus 1 artificial variables to the master problem. Then use phase 1 of the two-phase method, minimize the sum of the artificial variables to get a basic feasible solution to the original master problem. Okay? Remember, we've got a number of problems on here. We've got 3 problems. We've got the original problem, which we don't deal with directly. We transformed it into 2 problems. One is the master problem, which is the working problem that we actually try to solve. The other one is the subproblem. Subproblem keeps changing because the objective function coefficients are defined by WA minus C. And when W changes, of course, the objective function coefficients change. So the subproblems, they keep changing. And for the master problem, we have all the basic columns available, but all non-basic columns are sort of behind a curtain. You don't see them. What do? You fetch one by solving the subproblem, and you extract the appropriate column and insert it into your master problem. That's the main methodology here. Okay? And so, anyway, that's the situation. Maybe you need an example to sort of relate to what's going on, because I started seeing some puzzled looks here. Okay, let's look at an example. Okay, this is the problem, the original problem. Of course, you can solve this easily by just using the simplex method, but the idea is how we would use decomposition to solve this problem. So what I'm going to do is I'm going to isolate this part as my ax less than or equal to b part. This is the ax less than or equal to b portion. The remaining portion, including the non-negativity, is your capital X. So this part is your capital X. And in fact, if you look at the problem here, the non-negativity, we always deal with it on the side. So this part will lead to a subproblem. And the subproblem will have two independent subproblems, actually, because the special structure in the matrix tells you that that's what's going to happen. If it doesn't tell you yet, you will see that that is the case. Okay, so X is in fact the cross product of two sets, X1 and X2, where X1 is the feasible set associated with the first two constraints here. And X2 is the feasible set, again, in two variables associated with the second part here. So let's just plot these. If you look at the constraints, the first two constraints in the lower portion, it's going to tell you in the x1, x2 plane that you have a feasible set that looks like this. Okay? You have a simple lower bound constraint or upper bound constraint. So this is the extreme point, 2, 0, which tells you x1 is less than or equal to 2. The other one is the second constraint, and it goes like this with an extreme point here, which is what? 0, 5 over 2. And this point is 2 and 3/2. This is, of course, the origin. And that's your x1 set, okay, feasible, relative to the first two constraints. The second one, it looks something like this in the x3, x4 plane. This point is 0, 2. This point is 4/3 and 10/3. And this point is 3 and 0. This is 0, 0. Okay. So X is the cross product of these two feasible sets. And the master problem in this case is the following. It's going to be minimization of Cxj or C cap times lambda j. J going from 1 to t. I don't know what t is here. Well, you can compute it by looking at the picture, but in general, you will never know. Okay? So the constraints will look. This is the inequality version. So ax less than or equal to b translates into a times xj lambda j, j going from 1 to t equals b and lambda j adding up to 1 with slacks and lambdas non-negative. That's your master problem. So I need a basic feasible solution to start with. In this case, it's easy. If you take x1 to be the extreme point, which is the composition of the origin from the first one and the origin from the second one, it's going to have 0, 0, 0, 0. Okay? That's your extreme point for the four-dimensional set. In this case, of course, A times x1 is simply, well, it's going to be less than or equal to 2, 3, which is the B vector here. Because this part, when x1 is 0, is simply the vector of zeros. Okay? 0 and 0. So it does satisfy the condition that we looked for. So my initial basis or initial basic variables are slack 1, slack 2, associated with the master problem constraints. You've got two constraints here. As many as you have in the original problem. Okay, so S1, S2, and lambda 1 is your are your basic variables. So if you suppress all the non-basic variables in the master problem, the constraints will give you the following. What are the constraints? S1, and then S2, and then lambda 1. The last constraint is the sum of the lambdas adding up to 1. So lambda 1, the other ones are 0. So the last constraint is this. What about the first two constraints? Actually, it will be 0 times lambda 1 because A times x1 is a vector of zeros. Okay? And then another 0, lambda 1 here. 2 and 3, right? Equals 2 and 3. That's the way the constraints will look in the master problem when all non-basic variables are taken to be, or taken out of the problem, or if they are taken to be 0. Okay, so this simply gives you the solution: 1 for lambda 1, 2 for S1, 3 for S2. And of course, the basis is the identity here. So the inverse is also the identity. What about W alpha? It had 0 in CX1. If you recall, CX1 in this case will be 0. So everything is 0 here. Okay? And the objective value is also 0, right? Yeah. That's the initial tableau. All right. Maybe we should take a 10-minute break and then we continue, okay?